Okay, guys, let's have a look at 1436. If the 60 kilogram skier passes point A with a speed of 5 meters per second, determine his speed when he reaches point B. Also, so that's question 1, determine the speed at B. Also, find the normal force exerted on him by the slope at this point. Okay, so what do we have here? We've got some force information, we've got mass, we have velocity, okay, and we've got some position or height information. So we can use the principle of work and energy, half mv1 squared, or let's put it half mva squared, plus the sum of all the work done of the forces acting on the particle from A to B, actually that should be A to B, is equal to half mvb squared. Alright, so the first thing that we should actually always do is draw the free body diagram. So if there's the skier, remember this second term here is the work done by the forces on the particle as the particle moves from 1 to 2 or from A to B. Okay? So what are all the forces acting on the skier? Well, we've got the normal force. Okay, so the normal force would be acting there, and we have weight acting straight down. Okay, those are the only two forces. Okay, we're not considering friction. Okay, so it says neglect friction. So the only two forces we're considering are normal and weight. So in this second term over here, the only two forces that we would consider doing work are these two forces. Okay, we'll get back to that in a second. So what do we have here? We have half times 60, and this is 5 squared. Now, and then over here we're looking for this VB, right? So this on the right hand side will be half also times 60 VB squared. So we're looking for this VB. Now, this skier is moving from A to B. The direction of motion is always tangent to the curve. Wherever you are on the curve, the velocity would be tangent, or the direction of motion, or the displacement vector is tangent. All of those are tangent to the curve. So does the normal force do work as the skier moves from A to B? No. Why? Because the direction of motion is perpendicular to the direction of the force vector. And we know the dot product, cos of 90 degrees gives us 0. So these two vectors are perpendicular. The normal force does no work. What about the weight? The weight also applies a force as it moves from A to B. Okay? And we've got the weight times delta y. Okay? And we know that the weight, let's put a minus there because the weight is acting down. And what is delta? Delta y is the change in height. And so this is final height minus initial height. So let's see. Let me just, I'll just leave this here because I haven't done this yet. So we can just bring that down. We got minus 60 times 9.81. What is the final height? That's the final height. And how do we determine what the height is at B? How do we determine that? We have this equation of the curve, and we know that x equals 0 at B, so we plug x equals 0 into here, and we get y equals 5. So the height over there is 5. So the final position is 5. The final height is 5. Initial height is 15, so you're going to have 5 minus 15. And on the right hand side, we will bring that down. Okay, so we got this half times 60 times 5 squared, And what you notice here is that we have a minus here and we have a minus in the brackets. Okay? And so a minus times a minus would give us a positive. And does that make sense that we have positive work due to the weight? The weight does positive work. Does it make sense? Yes, it makes sense, because the weight is acting down and the displacement is down. So we have both the weight and the displacement vectors in the same direction. So we're going to get positive work due to the weight. So I'll just bring this down here, times 9.81 times minus 10 equals 30 VB squared. Okay, then you just solve this and you'll get VB is equal to 14.87 meters per second. That's what I got. Okay, so what's next? The next thing is determine the normal force exerted on him by the slope at this point, which is B. Alright, so if another free body diagram, we're going to have the normal force. This is at B, right? And then we're going to have the weight acting down. And then we know, if we use Newton's second law, we know that the sum of the forces is equal to mass times acceleration. But if we choose that to be our normal direction, and that's our tangential, if we're using normal and tangential components, then we have normal minus weight is mass times v squared, if we're looking at some of the forces in the normal direction. Okay, is equal to mass times acceleration in the normal direction. This is v squared over rho. Alright, so the normal force is what we're looking for. Here we've got 60 times 9.81. There's our weight. We've got 60. What's our velocity? It's 14.87 squared divided by rho. But what is rho? Recall that rho is given by, let's see, it's given by this equation, 1 plus dy dx. That squared, that whole thing, the whole numerator to the power of 3 over 2 divided by d2y dx squared. Okay, so all you need to do is take this equation, calculate dy dx, calculate d2y dx squared. Okay, put those in there and then plug in the value of x equal to 0. Alright, because we are at this point here where x is 0, and we would get rho is equal to 1 plus 0 to the power of 3 over 2 over 0.5. Well, obviously at x equals 0 has been substituted in, and this gives us a radius of curvature of 20. So we plug that in there and we get n is equal to 1.25 kilonewton. Okay, hope that was fun. Let me try to kill this video. Cheers.